All right, let's take a look at one more thing related to threads and using threads safely, and that is thread safety. So if we're going to use a function inside a thread, the function needs to be thread safe. Uh, Thread safe means it will produce correct results when it's called repeatedly from concurrent threads, even if it's called um, concurrently. So even if one call to that function happens while another call to the function from another thread is still going on. So there are, rather than talking about what makes a function thread safe, though, let's talk about what makes a function thread unsafe. And then a thread will be thread safe if it doesn't do any of those things. So class 1 would be a function that uses a shared variable, so a global variable or a static local variable, without protecting it with a mutex. Class 2 are functions that have state that's maintained across multiple invocations, so like a static variable, for example. And class 3 are functions that return a pointer to a static variable. And, of course, if a function calls a thread unsafe function, then that first function also becomes thread unsafe transitively. So let's take a look at those classes. So class 1 of thread unsafe functions is where they use shared variables and don't protect them with mutual exclusion. So as an example, that thread function in bad count that was referring to the global variable count was thread unsafe because those two different threads were using that global variable without doing synchronization. And the fix for that is to use semaphore operations or some other kind of mutual exclusion to make sure that doesn't happen, as we saw in good count in the last video. However, there's a problem with that in that doing synchronization slows down the code because threads will have to wait for other threads to release the mutex. And while a thread is waiting, while it's calling the P operation, waiting for the other thread to call V and unlock the mutex, it's not making any progress. It's just sitting there. So class 2 is kind of related, but there's another way to solve it. So those are functions that have state that persist across multiple function invocations. That could be with a global variable. It could be with a static local variable. So here's an example. This is how the rand function, to generate a random number, might be implemented. The actual implementation in your C library is probably not quite this, but this is something called a linear congruential random or pseudo-random number generator. It works by having a seed or having a state, which is called next here. When you call srand, that seeds the state with a particular value. And then every time we ask for a random number, we do some operations on the state, on that next, assign it into the next, and then we return the new value. Actually, we take some of the bits of the new value, shift them around. This is a division by a power of 2, so really a shift, and mod 32768. So the return value is always between 0 and 32767. So this is how the rand function was classically implemented. The problem here is that if two threads are calling rand at the same time, they might pick up the same value of the next variable and return the same random number. Maybe that's what you want, but that's also not guaranteed to happen. It could be that one finishes before the other does, and it could actually be even worse than that. It could be that, probably not, but depending on optimization settings and so on, it could be that this happens in multiple steps, and some of those steps involve storing things back into memory. And as that's happening, if we interrupt that with another thread, which is doing those same operations, we could end up not even having done this operation at all. We could end up with completely the wrong thing. So the solution for something like that, a function that requires persistent state, Of course, we could do locking, but a solution that doesn't require having that doesn't require adding in those P and V operations and slowing down the code would be to pass that state as an argument rather than having it as a global variable. Pass it into the function, and if we do that, then each thread could call srand on its own. The programmer has to keep track of the seed, and the programmer just passes that seed or a pointer to that seed into the function. So this is called rand_r. R here stands for reentrant, meaning it's okay if we call it while it's already in the process of being called. And this is a function in the C standard library. If you're doing random numbers in threads and you're using the C standard library, then rather than rand, you want to use rand_r. As far as that seed, we wouldn't call srand. That's modifying that global variable, but instead we would just set the value that this seed pointer points to before the first time we call rand_r. And we could set that to different values in the two different threads to make sure that they get different sequences of random numbers. Or if we want them to have the same sequence of random numbers, we could initialize them to the same value. Now, I said it's part of the standard library. It's actually not standard C, but it is standard POSIX, meaning on any Unix system, at least in a Unix system since 1995 or so, or that follows the version of POSIX that was introduced in 1995, then you have access to this rand_r function. And there are lots of standard library functions other than rand that have an _r version, a reentrant version that works a little bit differently, perhaps by passing in a argument that holds that state. All right, class 3 is when we have a function that returns a pointer to a static variable. So one example of that is ctime. So ctime takes a time t, which is a value representing the current time. On Unix systems, on Unix systems, usually that's measured in it's a long measured in seconds since the beginning of the Unix epoch, which is January 1st, 1970, midnight, the beginning of January 1st, 1970. But it's just an integer. We pass in a pointer to the integer here, and it returns a character pointer that will hold that time converted into a string. So rather than some big number, will return a readable version of that. The problem here is it's returning a char star. It's returning a character pointer. Where is the array that pointer is pointing to? Well, it turns out that's a static variable, either a static local variable inside the ctime function or a global variable defined in the same file as ctime. But either way, it's returning a pointer to some memory, and there's only one copy of that memory. Under normal circumstances, if I'm not using threads, that's fine. I would take whatever ctime returns, do a stir copy of it, or a mem copy, for example, to put it into another buffer after the return, and then I'm good. But if I'm calling this concurrently from two different threads, they're going to overwrite each other's strings. And depending on how those instructions in those functions get interleaved, it could be potentially really bad. I could end up with a string that has part of one time and part of the other time in the same string. Or I could even end up with something where the null pointer just gets put in the wrong place, or the null pointer that was supposed to be put there by one of the threads gets overwritten by the other one, and I have an unterminated string, and when I use it, I potentially get a crash. Um, there is a ctimr function. The idea here is rather than using a buffer that belongs to the ctime function, of which there's only one, we'll pass in the buffer. And then the time, the string version of the time that it computes will be stored into that buffer. We'll still return a pointer to the beginning of the buffer, just so we don't have to modify calls to the function too much. So now our callers will give us different buffers, and as long as they're not passing in a shared variable as the buffer, they won't interact with each other in a bad way. So that would be one. That would be one fix. The other fix would be to do a lock, call the function, copy the variable out, unlock, and then we can return that. We can return the pointer to that private variable, to that copy of the memory. However, in that case, the caller is responsible for freeing it. So a couple of different ways we can avoid thread unsafety and make a thread safe version of the same function. And of course, class 4, if a function calls a thread unsafe function, then it's also thread unsafe. The fix to that, it's kind of silly. Don't call thread unsafe functions. Okay, so I mentioned that _r stood for reentrant. So we say that a function is reentrant if it doesn't access any shared variables when it's called by multiple threads. So this is a subset of thread-safe function. Thread-safe functions could use synchronization instead, a semaphore. A reentrant function is nice because it doesn't need that synchronization. It doesn't need a semaphore. And remember that semaphores involve, and other forms of mutexes involve waiting for the other thread to finish what it's doing, meaning it takes extra time. So if we can avoid those synchronization operations, that's great. And that's what those _r functions are about. So again, out of all of the functions in the world, some of them are thread unsafe, some are thread safe, and of those thread safe functions, some of them are reentrant. So in the standard C library, so these are things not necessarily in Unix, but available in all C programs. Those functions are thread safe. malloc is thread safe. Of course, malloc is using this global heap, which is shared, meaning in a multi-threaded program, malloc has to do synchronization, which can slow it down, but at least that lets us use it. It would be pretty tough if we weren't allowed to allocate memory inside a thread in a multi-threaded program. Likewise, free, printf, scanf are all thread safe. Most Unix system calls and library functions are thread safe, but there are a few exceptions. So ctime, we saw, ASC time, ASCII time is similar. There are reentrant versions of those. Get host by @ or get host by name. Well, remember, those return a pointer to a linked list of things. Those are actually thread unsafe, but there are reentrant versions of them. Get host by @ or _r, get host by name _r. The older, so an older thing, inet into a, which converts a numeric IP address into an ASCII version of the IP address. There is no reentrant version of that, but remember that's what get adder info does if we pass it the right arguments. So get adder info is thread safe. Local time is kind of like ctime, but rather than returning a string representation, it returns a struct. Actually, a pointer to a struct that's a static variable. So we need to use local time r. And rand is another one with the same problem. It has this reenter version, rand_r. All right, so let's take a look at a couple of the issues that could occur in multi-threaded programs. So races. So a race or a race condition happens when the correctness of the program depends on what order the threads happen in, or that a thread, one particular thread gets to a certain point before another thread gets to a different point. And we saw some examples of that. Bad count has a race condition. So here was something in that shared shared.c example, or sharing.c rather. I mentioned that it has a potential problem that doesn't necessarily come up often, but there is actually there would be a race condition here on the I variable if instead of casting I to avoid star, just pretending it's a pointer, we actually did pass a pointer to it. If we did that, then both versions of, then this is a local variable inside the main thread. Both threads that are started would refer to the same variable. The problem there is if a thread accesses I before it's incremented here, that's fine, but the thread might not get a chance to dereference that pointer and get its value of I until after the main thread has incremented it already. So if things happen in that other order, we could have two different threads that have the same ID. That would be a problem. And we don't have an example program for that in the code, but if we were to write this out, then sometimes, not often, but sometimes, those two different threads could, or those multiple peer threads, could end up with the same version of the variable I. So the way we eliminate that is, well, as we saw back when we took a look at the echo server, we get some memory that won't be shared. So we make sure that each thread gets its own memory that holds that variable I, or gets a pointer to its own copy of that variable, and then they're not going to step on each other's toes. And then finally, the last kind of problem that we might see, which I mentioned in the concurrency videos, is deadlock, which is when a process is waiting for something to happen that will never happen. So if process 1 and process 2 both need two resources, so they both need A and they both need B. Those might be two different global variables, for example. We use mutual exclusion to protect those global variables, but what happens if process 1 acquires A, so it takes the lock, and then it tries to acquire B. Process 2 acquires B, takes the lock, and then tries to acquire A. So process 1 has the lock for A and is waiting for B. Process 2 has the lock for B and is waiting for A. Neither of them will be able to make any more progress because each is waiting for something that is locked by a process that is itself waiting for something belonging to the other process. Both of those processes will wait forever. So to look at that in a process graph, so we have those two resources, A and B, or here S0 and S1. They each have a forbidden region. And remember, as long as we don't go into the forbidden region, we don't have that problem where they're stepping on each other's toes. But if we were to wind up here, which we can do by following a sequence of right and up moves without actually getting into the forbidden region, now we have a problem because the only place to go from here is a forbidden region. Once execution of the code gets into this deadlock region, we have a problem. We'll eventually end up in this deadlock state. nothing else will happen. Um, and unfortunately, deadlock is non-deterministic because it could happen that we got up here instead, at which point we're fine, or we got over here instead, at which point we're fine. So what you would see in a program that has this problem is every once in a while, sometimes when you execute it, it just freezes up. Most of the time, it seems to work okay. And that can be a difficult problem to track down. Although once you see a program hanging, that might give you an idea of what's happening, and if you can look at it in the debugger, get it to hang while it's inside the debugger, you might be able to see that each process is waiting on a lock, and you might be able to see that the other process has that lock or that mutex. So how do we solve it? Well, the idea is we acquire those resources always in the same order. So the problem here was when process 1 acquired A and then waited for B, process 2 acquired B and waited for A. If we make sure that those two processes, each of those two processes acquires A first before it tries to acquire B, then we'll avoid that situation because that gives us a graph something like this. We've extended the forbidden region down. So instead of looking like this, it looks like this. And now there's no way for the trajectory to stop. There's no kind of corner here where where the only place we could move it would be into a forbidden region, which we can't do. So the way to do that again is to make sure the processes acquire the locks in the same order. The actual order in which they're released doesn't matter. That would just affect how far to the right or how far up these boxes extend. But remember, the problem is when we have a notch like this towards the lower left, or when the resources are acquired in different orders. Okay, so that's all for synchronization and concurrency, and in fact, that's all for the class this semester. So I'd like to thank you all for bearing with me. This is my first time teaching an online class, as I mentioned when we first started with the online classes. So I know it's been a challenge for everyone. It's been a challenge for me as well. Thank you for your patience. Thanks for your attention, and good luck on the final exam next week.